In this video, we will discuss why and how we should test for a three-phase unbalanced system. Also, we will discuss the effects of an unbalanced three-phase system. Commercial equipment 5 horsepower and over are electrically three-phase powered. When this power is unbalanced, it can reduce the motor's life due to overheating of the windings. It can also lead to the motor's downrating of its horsepower. When installing or servicing three-phase motors or compressors, it is important to check for an unbalanced condition. Let's look at the source of the three-phase power. This drawing depicts a 4-wire three-phase power system. The configuration is called Y because of its shape. A Y connection is a 4-wire connection. Two types of Y connections are possible: a 4-wire three-phase system and a 3-wire three-phase system which has no neutral. Out of the 4 wires, 3 wires are phases and 1 wire is a neutral connected at the common point of the 3 wires. This drawing depicts a three-phase power system. The configuration is called delta because of the shape as a triangle. A delta connection is a 3-wire connection. In a delta connection, only 3-wire three-phase system is possible. All 3 wires are phase wires in a delta connection. In a delta connection, every wire is connected to an adjacent wire in the form of a triangle. All of the 3 common of the connections form the 3 phases. There is no neutral in a delta connection. Three-phase motors used in many HVACR applications are designed to run on three-phase alternating current. AC electricity changes directions from negative to positive and back 60 times a second. AC changes power in a smooth, continuous wave called a sine wave. Three-phase AC has 3 sources of AC power, all out of phase with each other. That means that no 2 AC waves are ever at the same point at the same time. In this diagram, each of the 3 phases shows a separately generated voltage. A sine wave may be produced with 1 revolution of the generator, 360 degrees. The A phase starts at 0 degrees, peaking positively at 90 degrees. It passes through the 0 volts again at the 180 degree mark and peaks at the 270 degree mark. After it peaks negatively, it returns to the 0 volts at the 360 degree mark, which is also the 0 degree point. The B phase does the same as the A phase, except it starts 120 degrees later. The C phase does the same as the A phase, except it starts 240 degrees later. What causes a balanced or unbalanced three-phase? The source or the load? It is not the source that decides whether the system is balanced or unbalanced, which we define as the generator or distribution system. It is the load which decides whether the system is balanced or unbalanced. The most likely cause is unbalanced single-phase loads on a three-phase service. Three-phase voltages or currents are displaced from each other by 120 degrees. Let's look at a Y-connected source. Let's connect the source to an equal load. Since the loads on the system has equal current on each phase, the load is balanced. The properties of a balanced system are: the waveform has a perfect shift of 120 degrees. The current flow through each phase is identical. No current flow through the neutral. Low or no power loss. Most of the systems are unbalanced, and the properties of an unbalanced system are opposite of what we just stated. Let's look at a three-phase unbalanced system. In the drawing below, I have increased the load on one phase. This will increase the current draw more than the other two phases. This condition causes a power loss in the system. Let's take a look at some of the causes of an unbalanced system. The source of the voltage from the electric utility is unbalanced. This very rarely happens. Unequal impedance of the three-phase distribution system. Unequal distribution of single-phase loads. Unbalanced load across each phase. Mismatched transformer taps. Faulty contactor loose connections, and this happens quite often. Single phase loss, which means that one of the phases is out of the circuit. Talk about quantifying the losses of an unbalanced system. NEMA standard for electric motor recommends maximum voltage unbalanced to be 1% without derating the motor. Above 1% voltage unbalanced, motor rated horsepower needs to be derated. Voltage unbalance leads to current unbalance, overheating, damage, or reduced life in induction motors. Motor temperature rise of 50 degrees Fahrenheit above the rating will reduce motor expected life by 50%. If a very high current unbalance is present without a corresponding voltage unbalance, then this could be a sign of a fault in one of the three phases above 5%. Let's look at the procedure for testing voltage unbalance. Unbalanced voltage tests should be performed when the compressor or induction motor has multiple trips on overload. Unbalance should be within 1%. Check the voltage on each phase of the power source. First test line A to B. 230 volts shows on our meter. Next, test lines A to C. 228 volts shows on our meter. Next, check voltage between B and C. We show 230 volts on our meter. The formula to calculate voltage unbalanced is percent of unbalanced is equal to the maximum voltage deviation divided by the average voltage times 100. I'm showing the average voltage from the three readings in the previous slide of 230 volts, 228 volts, and 230 volts. Adding those together, I came up with 688.0 volts divided by 3, which equals 229.3 volts, which I will round out to 229 volts. The difference between the average voltage and the measured voltage is, from A to B we had 230 volts. We're going to subtract 229 volts, which said we had 1 volt deviation. From A to C, we had 228 volts, which we will subtract 229 volts, which is equal to minus 1 volt. From B to C, we had 230 volts, minus 229 volts is equal to 1.0 volts. Therefore, the largest number there was 1, so the maximum deviation is 1 volt. Using our unbalanced formula, let's fill in the numbers. The maximum voltage deviation is 1, and the average voltage is 229. Doing the multiplications and division, we come up with 0.4. Therefore, the unbalance is 0.4%. Since this is within the 1%, it is acceptable. When a compressor or induction motor has multiple trips on overload, you should test for current unbalance. The unbalance should be within 5%. In this example, I have shown the current draw on each leg of the compressor or motor, T1 at 25 amps, T2 at 27 amps, and T3 at 26 amps. The formula to calculate current unbalance is percent of unbalance is equal to the maximum current deviation divided by the average current times 100. To calculate the average current, we add our three currents together and divide by 3. From the previous example, we show T1 is equal to 25 amps, T2 is equal to 27 amps, T3 is equal to 26 amps. Adding those together, we come up with 78 amps divided by 3 is equal to 26 amps. The difference between the average current and the measured currents is T1 is 25 amps minus 26 amps, which gives us negative 1 amp. T2 is equal to 27 amps minus 26 amps, which is equal to 1 amp. T3 is equal to 26 amps minus 26 amps, which is equal to 0 amps. Therefore, the maximum deviation, which is on T2, was 1 amp. We can now calculate the percentage of unbalance by filling in the values from the previous example. The maximum current deviation was 1, and the average current was 26. Filling those in and doing the math, we come up with an unbalance of 3.8%. Since this is within the 5%, is it an acceptable amount?